everybody. We are very happy to see all of you here today. So even if virtually, but anyhow, it's really a pleasure. So just so this is the second ECOS ANID workshop in algebraic geometry. We had the first one last November, but this is more international somehow, because also a follow-up activity of our Women Algebraic Geometry, who is a lecture we had with Paula last year. And we have several participants from this school also, and also in the framework of the ANR, Symmetry and Modular Space in Algebraic Geometry and Physics. So there are several different aspects in this workshop. And well, let's start. So we start with the first speaker today, who is Nathan Priddis from Provo, USA, who will talk about non-symplectic automorphisms of K3 surfaces, uniqueness, and invariant lattices.
Right, I'm going to start sharing my screen just a second. There we go. All right, thank you, organizers, for the opportunity to give this talk. I have to excuse my voice a little bit. I was at the theme park 2 days ago and I did a lot of yelling. So hopefully it's okay. And this is my first talk by Zoom, so hopefully that will go well as well. Sorry. So my title is Non-symplectic Automorphisms K3 surfaces. I think Alessandra said a few more words on there too, so those are all in my talk too. What I'm going to talk about is mostly joint with our organizers, Paula and Alessandra. But let me just jump right in. So this is kind of what my talk is going to be like. I'm going to give a little bit of introductory slides, and then we'll talk about K3 surfaces when they're sort of determined by certain non-symplectic automorphisms. And I'm going to especially focus on order 16, which is where our work was in a recent paper. And then I'm going to talk about, at the end, a little bit about their invariant lattices. So here we go. First of all, definition is the K3 surface. It's a compact complex surface S with the irregularity should be 0, and there should exist a non-vanishing global 2 form, which we're going to call omega S in this talk. We're going to see that several times later. Maybe that means the geometric genus is 1. And also, I'm not going to keep writing this, but for the rest of the talk, whenever I write S, I just mean a K3 surface. The second thing, excuse me, an automorphism. So automorphism of K3 surface should just be a biholomorphic map from S to itself. But we're in particular interested in certain kind of these. We say it's symplectic if the induced map on the 2 form is trivial, and therefore it's non-symplectic otherwise. Right? So it's going to act on this 2 form by some non-zero and, well, not the identity, some complex number. Mostly we're interested in this last one, which is purely non-symplectic. So we say purely non-symplectic. I probably should have written this in the wrong order. It should be pure non-symplectic of order n. So this sigma is purely non-symplectic of order n if the action of the volume form is by a primitive nth root of unity. And this here, usually we think of e to the 2 pi I over n. Oh, I was also going to say, whenever I write, so for the rest of the talk, I'm not going to always write this, but for the rest of the talk, whenever I write sigma, sigma is going to be an automorphism of S. Excuse me. So a couple of things that are important also later in this talk. Well, what it talked about invariant lattice. So what is a lattice? So lattice is a free abelian group of finite rank, and it's got a symplectic bilinear form, which here I'm writing B. I might not always write B in this talk, so hopefully it's clear. Lattice is even if I stick the same thing in both spots on B, I get an even integer. The signature of a lattice is just the signature of the bilinear form. And this last one's a bit of an important definition. we say in embedding, so if M is a lattice and L is a lattice, you can often embed a lattice. Let's say M embeds into L. This embedding is primitive if the quotient is a free group. And this last definition down here is not so important for this talk, but it is important for sort of the work, the discriminant group. If you take a lattice, you can embed it into the dual lattice, which is homomorphisms from L to Z, via this bilinear form. And then if you take the quotient, that's always a finite group, which we call a discriminant group. Most importantly for this one is that a lattice is unimodular if that finite group is trivial. And then well known is that for all K3 surfaces, the second cohomology group is always this particular lattice. If you, the bilinear form is via the cup product. And in case you haven't seen this before, U, when I write U, here I wrote U as a matrix. Again, it should be a free abelian group. So here I mean a free abelian group of rank 2. And if I pick 2 generators, so I think of this as Z2, the bilinear form can be given by this matrix. And again, if you haven't seen this before, E8 is it's a negative definite lattice of rank 8. And here I've drawn a diagram. So let me just quickly describe how to get from this diagram to a lattice. That is, if you think of each of these nodes here as a generator. So here you can see I've got 8 nodes. So it's a free abelian group of rank 8. So thinking of each of these as a generator, and you can tell quickly if I write B as my, let me call this one, just call this one X and maybe this one Y, and say B of X. If I pick any of these generators, well, actually let me just call that one X. Any of these generators, if I put it into the bilinear form, both entries I get a -2. And if 2 nodes are connected by an edge, then those, if I put, so let me call this one Y. If I put, for example, BXY here, I get 1 because they're connected with an edge. If they're not connected with an edge, then I get a 0. So that's how you get a lattice out of this diagram. So again, the upshot on this slide is that the second cohomology group is always this lattice. And this is a very well-known result. There's a couple of important sublattices here that we want to talk about quickly. The first one is called the invariant lattice. So if I take, again, as I mentioned before, sigma is an automorphism on S. So I've written the invariant lattice as S of sigma, but it's just all the classes in H2 that are fixed by the induced action by sigma. And if sigma is purely non-symplectic, say of order n, then this invariant lattice actually sits inside the neuron-severe group. And the second lattice that would be important for this talk is called the transcendental lattice. It's just the orthogonal complement of the neuron-severe group. Again, it's the orthogonal complement in H2 with respect to this bilinear form. And if sigma is purely non-symplectic of order n, then the transcendental lattice is orthogonal to the invariant lattice. So that's the end of the introduction. Now I'm going to talk about some important and interesting results that talk about when purely non-symplectic automorphism actually determines a K3 surface. So this is a result by Simon Brandhorst. It says, if F is purely non-symplectic, I probably should have written of order n here. Just let me add that. So you can see if sigma is purely symplectic of order n, then phi, but here phi means the Euler-Totient function. So phi of n always divides the rank of the transcendental lattice. And this theorem by Simon Brandhorst, we're going to ask, well, what if the rank is exactly phi of n? So The theorem says if S is a K3 surface, again, sigma is purely symplectic of order, purely non-symplectic of order, purely non-symplectic of order n. And if we require that the rank of the transcendental lattice is phi of n, and this primitive nth root of unity is not an eigenvalue of phi, of sigma on the Néron Severi group. So what this means is kind of, you can think of the action, if I tensor with C on H2, I come back to this invariant lattice, you want to think of kind of as is related to the eigenspace of sigma star with eigenvalue 1. And the transcendental lattice is always related to the eigenspace of the primitive nth roots of unity. So what we're requiring here is that all of the primitive nth roots of unity, so the eigenspace is basically in the transcendental lattice. Anyway, so I'm going to pick out one other number here. It's called we're calling it D on this slide. It's just the determinant of NS. If you come back to, let me go back a minute. Come back to this discriminant group. D is the order of this discriminant group, basically. S is determined up to isomorphism by the pair, by these two numbers, N being the order of the automorphism and D being some data from the transcendental lattice. So this is a pretty interesting, I think, an important result. There's a couple of other things I want to say about this briefly. And the first is if phi of n is bigger than or equal to 12, it turns out the automorphism is also uniquely determined. So there's only one K3 surface and only one automorphism satisfies, well, okay, have to be a little bit careful because sometimes there's two. For example, here in this line, you see this 28, I've got the same surface twice, two different automorphisms. But anyway, these are all of them. These are all of the options with n if phi of n is bigger than or equal to 12. All the K3 surfaces and all the non-symplectic automorphisms that there are, satisfying these conditions. But more interesting, there's if phi of n is not, well, it's less than or equal to 12, then the K3 surface is still unique, but we don't necessarily know about the automorphism. So I say sigma is not necessarily determined by this data. There are a couple of things to say about that, however. In this case right here, this first one I wrote down here, for these two cases, 16 2 to the 4th and 24, I'm sorry, 2 squared and 24 2 squared. I've written them in green so you can see them kind of here and here. And oh, I should say also in these tables, let me just mention this also. In these tables, what I've given here is some way to describe X. Oh, X should be S. All right, copy this off. Some way to describe the K3 surface. So most of these are what's called an elliptic surface, and I'll talk about that in a minute. I didn't give the automorphism in this table though. But anyway, so if you look at these green ones here, since the automorphism group of the K3 surface is just Z mod and Z, turns out the non-symplectic automorphism is unique. But if you look on for example, these blue ones, so this surface here and here and here, Braunhorst's paper, he lists an automorphism, but it turns out there's at least two. Well, I mean, okay, so there's basically exactly two. This is the automorphism group is Z2 mod, Z2 cross C to the N. So we have some results for these 5 surfaces about whether the automorphism is unique or not. But for the rest, the automorphism group is infinite. So we don't really know much about whether sigma, the purely non-symplectic automorphism, is unique. So I'm going to skip. I'm going to come now just to this bit of the table right here with 16, because there is another result that I want to talk about. It's by Altaba and Sarti. And we talked about order 16 automorphisms. And in their paper, they did a good job classifying sort of all purely non-symplectic automorphisms of order 16, but I'm just sort of zeroing in on the case that sort of intersects with Brandhorst's paper. So for order 16, just a little bit of notation so you can understand this theorem. I'm just writing for the rank of the invariant lattice is R, and n sigma is the number of isolated fixed points of sigma, and k sigma is the number of fixed rational curves. So in all of these cases, if you look at the fixed locus of sigma, it breaks down into basically you can have a curve with positive genus, and then you can have some number of rational curves, and then some number of isolated fixed points. So let me describe the theorem now. Excuse me. Let S be a K3 surface, and sigma again is purely non-symplectic order. Now again, I'm just focusing on order 16. And to put us sort of in the framework of Brandhorst's result, we're assuming that the Nearon-Severi group has rank 14. And if you think about last in the result by Brandhorst, remember we're asking about the transcendental lattice. So you'll notice hopefully that the rank of the transcendental lattice in this case therefore is 8, and that then puts us squarely in the result of Brandhorst. Anyway, then one of the following distinct cases holds. I've shortened their theorem here to fit it on this slide. Basically, the information I want to pull out of it is there's kind of two things can happen. You can either have a curve with genus 2 or 3 in the fixed locus of sigma to the 8. Now, since sigma has order 16, sigma to the 8th is a non-symplectic involution. So that's this one right here. Or one other thing can happen is that you get an elliptic curve in the fixed locus of the 4th power of sigma. And then in that case, well, in both of these cases, then you have the following data for your K3 surface. In the top two, you can see is belonging to this case right here, with the 3, 2, and 1, and the bottom two cases belong to this second case. I put these two in red because they actually weren't part of the theorem. These Nearon-Severi groups were part of the theorem, but these were calculated later. These Nearon-Severi groups here. One other thing to notice here is, right, you can see this one sort of is on its own. These two sort of suggest maybe those belong to a single K3 surface, and these two together also maybe suggest that they belong to a single K3 surface. Remember, there's only 3 of them after all. So anyway, this is their result. So now I'm gonna quickly describe each of these K3 surfaces. So like I was mentioning, there's one K3 surface with a purely non-symplectic automorphism order 16. It was here. There's one K3 surface with 2 purely non-symplectic automorphisms of order 16 here, and I'll describe those. And then the last one, we don't know from Brandhorst's result if there's just these 2, but we'll talk about that very last. Now, before I describe these surfaces, again, if you haven't seen this before, let me just quickly describe what an elliptic fibration is, because all of these surfaces are described by an elliptic fibration. So an elliptic fibration on S, again, S is a K3 surface for this talk. It's a morphism from S to P1 so that the generic fiber is a smooth elliptic curve. And it's called Jacobian if it emits a section, which is just a map backwards. Again, as usual, a section means that if I compose S and pi, I get the identity. Do it in the appropriate order. Another, if you've never seen this before, another kind of important fact is if you have an elliptic K3 surface, in other words, a K3 surface with an elliptic fibration, then your fibration has a positive finite number of single fibers. In other words, you always have singular fibers and you only have finitely many of them. And then I just threw this fact on just so you can kind of think about why these are purely non-symplectic. When I describe a non-symplectic automorphism, if you're bored, you can sort of check that it actually is purely non-symplectic by this volume form. It should preserve, or it shouldn't preserve the volume. It should have the overall effect of multiplying this volume form by primitive 16th root of unity. All right, so there's our elliptic fibration. Now I'll start. I'm going to describe all of these K3 surfaces to you. So you saw in Brandhorst's result, there's 3 surfaces. S has a purely non-symplectic automorphism order 16. Again, we're requiring that the rank of the transcendental lattice is phi of 16, which is 8. And the determinant of the Nernst-Severi group will be one of these, 2 to the squared, 2 to the 4th, or 2 to the 6th. And again, you can see those in this table here. This one has determinant 2 squared. This one has these two. This Nernst-Severi group has determinant 2 to the 4th, and this one 2 to the 6th. And just so you can compare it with what Brandhorst showed in his table, here's the first one belonging to here, and I'll describe it again in just a minute. Here's the second one belonging to these two, and the third one belonging to these two. Again, Brandhorst just listed one automorphism for each of these cases. I'm going to tell you all of them in just a minute. So here's the first one. Again, the equation is, well, you can read it there. Kind of more importantly is what are the singular fibers. From that equation, you can find out the singular fibers that's got an I0 star. And if you've never seen this before, I've drawn sort of the fibers here. So if you don't know what type I0 star or type 2 star are, don't worry about it. I've drawn them here. Again, if you've never seen elliptic fibrations before, there's only certain kind of singular fibers that can happen. There's a table of them, and they can be completely determined from the Weierstrass equation. So anyway, over 0. So this is my, in this picture, this is my P1 down here. And this is S up here, and this is my, I think of this as my map pi. So over 0, I've got an I0 star, which looks like this. In this picture, each of these curves here represents a rational curve, and they're sort of joined, or they have sort of intersections described here. So remember, the automorphism of group of this particular surface is Z mod 16Z. So there is exactly one, or depending on how you think of it, there's basically one purely non-symplectic automorphism order 16. And so it's this one and powers of this one are all of the purely non-symplectic automorphisms of order 16 on this surface. So what does this one do? If you want to pull this back, so I should be looking for 12 fixed points, 1 fixed curve, and a curve of genus 3. I haven't drawn the curve of genus 3, but if you sort of look through here, I've labeled the fixed points in red. So I should count 12 of them. Here's the fixed rational curve. It's one of the sort of the central fiber in this 2-star fiber over infinity. And this automorphism exchanges these 2 rational curves here. So that's the first one. The second one, again, you can read. Here's the equation. Again, more importantly is what are the fibers? What are the singular fibers? It's got a 3-star over 0, so that's this one here. And then it's got 5 fibers of type 3. One of them lies over infinity, and the others are, you can think of as sitting at the 4th roots of unity. So anyway, this one, as I mentioned before, has automorphism group Z2 cross Z16. And so there's 2 purely non-symplectic automorphisms order 16 on this surface, and I've listed them here. I'll talk about this one a little bit more later. So move on to the next one. This one I didn't draw, it didn't give a very good drawing for, unfortunately, but let me just kind of mention what's going on here. Here's the equation again. You can read it, x cubed plus x plus c to the 8th. What do we have for singular fibers? We have a type 4 star. So a 4 star is this black, sort of dark curves. That's what a 4 star looks like over infinity. And 16 fibers of type I0, and I0 is a nodal rational curve, so we usually draw it something like this. On this surface, however, we know that the automorphism group is infinite. However, I've still listed kind of two important non-symplectic automorphisms of order 16 here. There they are. And the question is, are there other purely non-symplectic automorphisms order 16 on this surface? And so that's the content of this slide here. The answer is basically no. And so let me tell you more details about that answer. Here again, I've listed those two surfaces. Oh, sorry, those two automorphisms. Those are sort of the two that we're going to focus on a little bit in this. But anyway, so what we find is that the automorphism group of S turns out has a really nice form, even though it's not just sort of these two purely non-symplectic automorphisms order 16, but it's also got all of sort of these, the Mordell-Weil group, which I won't describe, but it has to do with translation by sections. So anyway, this is sort of an infinite group and then a semi-direct product. Anyway, we say that. So what do I mean by these two? So when I ask the question, are these two automorphisms unique? What do I actually mean there? Well, basically, we're asking if I have another purely non-symplectic automorphism order 16, is it sort of a conjugate of one of these two? So anyway, we say that a surface, sort of this pair, a surface and a purely non-symplectic automorphism, and here the same thing. We say they're isomorphic if there's an isomorphism, sort of from the surface to X. So the way you want to think about this in light of this next theorem is, if X is also S, then this would be F would be a map from S to itself, and this would just be conjugation by F. But anyway, so that's what we're saying here. This is the theorem joint with Paula and Alessandra. If sigma is purely non-symplectic of order 16 on, again, this last surface that I described, then it turns out sigma is conjugate to one of those two automorphisms. So the answer is yes, there's only sort of one of each type. So if you kind of come back to this table, basically what we've shown is that there is exactly one automorphism of each of these types on these K3 surfaces. Okay, so that was the main result that I wanted to talk about. Now we'll move on to talking about a little bit about invariant lattices. So first of all, why do we care about invariant lattices? And for me, I think there's probably other answers, but for me, the sort of main answer I like to give is that they seem to be very important for mirror symmetry. So when you talk about mirror symmetry for K3 surfaces, the invariant lattice seems to be somehow the right tool for describing mirror symmetry. So what does that mean? I'm gonna put in two slides here that are kind of a little bit technical, and I'm not going to give all the background, but I just want to kind of give you a flavor for why we care about this in terms of mirror symmetry. So first of all, how do you describe mirror symmetry for K3 surfaces? Well, you start with what we call M-polarizable K3 surfaces. You can do this a little bit more precisely by giving an actual, if you talk about what is the actual embedding, and you include that in the data of the K3 surface. So if you talk about polarized K3 surfaces, that would include the data of this embedding. But We don't want to so much think about that. We just want to say, for the purpose of this talk, we just want to say, is there an embedding from S into the near severe group of your surface? If there is, oh, sorry, again, a primitive embedding. If there is, then we call S M polarizable. And so how does mirror symmetry for K3 surfaces work? Well, you start with a sublattice of the K3 lattice, should have signature 1T, and basically the idea is you want to think about X being M polarizable, and you want to think about, well, what's the mirror for X? In order to find a mirror for X for a K3 surface, you take the lattice that you were sort of using to polarize your first K3 surface, you take its orthogonal complement in the K3 lattice, and if you're lucky, you can write it as a copy of U, right? That's the same U that I talked about in the very first, plus something else. And this something else is called the mirror lattice to M. And so again, if you take X to be M polarizable and X prime to be polarized by the mirror lattice, then we say that X and X prime are mirror pair, like this. And so where does the invariant lattice come in? Well, there's another way to, for certain K3 surfaces, there's another way to talk about mirror symmetry. If you start with what's called a quasi-homogeneous polynomial, there's a famous list of 95 weight systems, so that your hypersurface in weighted projective space with respect to that weight system. So if you take a polynomial that's quasi-homogeneous with respect to one of these 95 weight systems, you'll essentially get a K3 surface. You have to blow up the singularities and things like this. But anyway, it's essentially a hypersurface in weighted projective space. And G is a certain group of symmetries. And from this data, you can build K3 surfaces. And if your polynomial happens to take this form, there's a certain purely non-symplectic automorphism on that K3 surface, which I'm going to call sigma sub n. If I look at that invariant lattice, the invariant lattice of that purely non-symplectic automorphism order n, then there's a way from this data to find a mirror pair, which I'm going to call X. So you get another polynomial in another group, and that will yield another sort of canonical purely non-symplectic automorphism order n on the new surface, on the mirror surface. And so if you polarize this one by this lattice and polarize this one by this lattice, then you get the two forms of mirror symmetry agree. So the upshot of this slide here, it's kind of technical and maybe you didn't understand everything I was saying, but the idea is, notice this invariant lattice is sort of the thing that's giving us the mirror symmetry. So the last thing I want to talk about is, well, how do you compute the invariant lattice on these particular K3 surfaces? So I'm just going to, well, here's the answer. In our paper, we also computed all of these invariant lattices, and hopefully it's okay that you can see, right, this 13 belongs with this line up here. This 11 and 7 are these two here. 9 and 7 are these two here. So how do we do this? Well, it's particularly nice. I'm just going to show you kind of on this one here, this second one that I described to you. Again, here's the equation. It had this kind of fiber over 0, and it had this kind of fiber over infinity, and sort of these 4 other singular fibers. So what I'm going to do is, for each of these, and again, each of these up here represents a rational curve. I forgot to mention these dots up here are sections. So what I'm going to do is I'm going to take each of those rational curves and put it into a graph down here. Sort of like the E8 graph we had at the very beginning. This will define us sort of a lattice. You have to be a little bit careful because some of these will be redundant. anyway, so hopefully it's clear. So like this curve right here is this node. This, let's see. Nope, sorry. This curve right here is this one. You see this one right here is this one because it intersects those three, which are those three. Okay, so this is how you do it. And this 2 here, I put on an edge because this is a sort of a double intersection. So I built this lattice here and turned it into a graph. And then we're going to ask, well, what does the non-symplectic automorphism do to this? So here's the non-symplectic automorphism. You can check. Again, it fixes all those blue dots that I wrote. It fixes this curve here, and it sort of permutes these amongst themselves like this. And so in the lattice, even though that, like, for example, this curve isn't fixed pointwise, it will be invariant under the action in IH2. And so what we've done is take this diagram, and I've sort of permuted all of these and replaced them by these right here. And so this square here should represent the sum of these 4 curves. And so this is somehow representing something to do with the invariant lattice. And now, if you remember, we want a primitive embedding. So it turns out the invariant lattice is a primitive sublattice of the near-Severi group. So what we need to do is find an embedding of sort of this lattice into there. Anyway, so what you do is you look at these curves and you find out by doing some linear algebra that these 3 here that I've sort of made hollow are linear combinations of the remaining curves here. And same thing up here. These ones that I've made hollow are linear combinations of the remaining ones. And so, so these curves here will generate a sublattice of the invariant lattice. And you'll notice the rank is 11, and there's 11 curves here. And so if the idea is if you can show that the lattice generated by these ones down here embeds primitively into the near-Severi lattice, then you've got yourself the invariant lattice. And so what I've done up here is, again, the same thing. You can very easily compute that those curves there are sort of redundant. They're linear combinations of the remaining. So I've given in these curves, these gray ones here, a generating set for the near-Severi group. And since these are a subset of that generating set, it's really easy to see from this diagram, therefore, that you've got a primitive sublattice. Anyway, so this is the way that you can, in this case, calculate the invariant lattice. Let me show you just one more quick thing here. The reason this is kind of interesting is in this example, notice we picked those generators for the near-Severi group, but that didn't work very well with that second automorphism. So that second automorphism on this particular surface, it's going to sort of permute all of these. Right? So it's going to send this one there, and this one there, and this one there, and this one back to here. Okay, so that first set of generators we picked for the near-Severi group isn't going to work to show that this was a primitive sublattice. And so you have to pick a different set of generators. So you pick these gray ones up here. If you pick this set of generators, then you can show that what I've got. So again, sort of do the same thing. I'm running out of time, so I want to describe this a little bit quickly. Do the same thing on this second K3 surface. Sorry, the same K3 surface, but the second non-symplectic automorphism. Again, I take all the curves and turn it into a graph. Then I ask, what does the automorphism do to the graph? Well, it's going to, so since it sort of flips these 2 up and down, so these 2 added together will give me this curve here. These 2 curves added together will give me this class here, etc. And so this is somehow representing, this graph here is somehow representing the invariant lattice, but again, there's redundant curves. There's too many. So I have to find out which ones are, I should have only 7. The rank is 7, so I need to find 7 curves that generate. And so it turns out I can get rid of those 2. but I need up here a different generating set for the neuron severity group to show that this is a primitive embedding. And if I pick this set of generators, you can see this curve right here is just the sum of those 4 generators. This curve right here is just the sum of those 2 generators. This one's the sum of those 2 generators, and so forth. And then you can see that just from these graphs that you've got a primitive embedding, and therefore you've computed the invariant lattice. Anyway, that's all I had to talk about today. Thank you for listening, and be happy to take any questions.
So thank you very much for your nice talk. So let's thank. So do you have questions or remarks? Comments? So well, maybe just one question from my side, because one can Kähler manifolds to do this mirror symmetry. I don't know if you ever thought about that, to do similar thing.
Sorry, say that again. You cut out right.
Considering EHS manifold, hyperkähler manifold, instead of 3 surfaces. And there you have also automorphisms that you can classify and study in somehow similar ways. And, there is some notion of mirror symmetries that was introduced recently. And I don't know if you ever thought about that.
I've given some little bit of thought, but not very much. I've thought about investigating it, but I haven't looked into it.
Okay.
So I think it will be interesting, probably, because there's some other things, some other things I'm interested in which deal with mirror symmetry. For like these hyperkähler manifolds, there's a certain some of them you can build some. So it comes from if you look back at this, I mean, I didn't describe very much on this slide, but when I talk about a group of symmetries here, this particular group had to be abelian. And so there's some interesting things you can ask about non-abelian groups and still build K3 surfaces or hyperkähler manifolds. I think there's something interesting to say there, but I haven't had time yet to look into that.
Okay, thank you. Are there more comments or questions? So if not, let's thank Nathan again